Welcome back. So section 8.3 really kind of ends what we are talking about with hypothesis testing. When we get to 8.4, we're going to do hypothesis testing again, don't get me wrong, but we're going to be dealing with two proportions instead of just one, as we have dealt with in 8.1, 8.2. And what 8.3 is, it just gives us a little bit of extra information, just some last minute tidbits and things like that. So let's talk about some of the bewares of hypothesis testing and refine our knowledge on it just a little bit more. Okay. So we have extreme stats. Okay. So what they're talking about here is they're talking about a relationship between the p-value and the z-statistic. And what we have found is the p-value depends on the observed outcome, what our sample does. Okay. So in other words, the larger the z-score, the more extreme that z-score is, the smaller you should be expecting the p-value. Okay. And that makes sense because when your value is extreme, okay, say we're doing a one tail over here, when my value is extreme, really, really far away from zero, in other words, the z-statistic, when that z-score is way out here extreme, the area on the curve is very, very small. Okay? And that's really about what the p-value is that area under the curve, the probability under that curve. Okay? So the further away from zero we are, the more extreme, the smaller the p-value. And vice versa. The closer you are to zero, the less extreme, the larger the p-value. Okay? So it's kind of like a sliding scale there. The larger your z-score gets, the smaller the p-value gets. And vice versa. The smaller the z-score, the more area, or the larger the p-value you have to cover. Okay? There are, I don't think it was time. Yeah, I was going to say, I skipped one. So when checking CLT, just some things about if conditions fail that I want to touch base with you on. Okay. So in the CLT, if your sample size is too small, I want you to know, if the sample size is too small, it doesn't mean that it means that it can't be a one proportion z statistic then, obviously, because it's not a normal distribution. Okay. But there are other tests that we can work with if the sample size is too small. Just so you know. Just because the sample size is small, we throw out the normal distribution, but that doesn't mean that it's all a lost cause. There are other tests out there. We're just not going to talk about those. It's not in our book. We don't have to worry about that part being covered. Another piece, if the sample size is not random, okay, then we cannot make inferences about the population. However, sometimes we're not interested in the population, just so you know. A big thing with this one is think about medical and psychological samplings. Generally, when it comes to medical and psychological samplings, they have to do a convenience. They have to have people that volunteer for this. So it's not necessarily random per se, because they have to have people that volunteer, or they have to seek out certain types of people. So say like you're studying the effects of drugs on insomniacs, okay? You have to physically seek out insomniacs as a medical professional who is trying to study the effects of this drug on insomniacs. So again, right there, I'm not talking about necessarily the effects of drugs on an entire people, but I'm talking about the effects of drugs on a certain kind of person. But more specifically, I'm not interested in the population. talking about something about that population. I'm more interested in knowing, did my treatment work or not? Okay. So that's what I'm saying. Even though the sample is not random, maybe per se, doesn't mean um, it means that we can't make inferences about the population. But maybe I'm not worried about the population. Okay. Maybe I'm worried about does the drug work or not? So just because the sample's not random doesn't mean, again, all is a lost cause, because maybe we're not worried about the population. All right. There are two types of mistakes that we have to watch out for when doing hypothesis testing. And maybe you thought about this, but maybe you haven't. And these two types of mistakes revolve around that significance level. Because remember, in the significance level, we run the risk of rejecting, we have a possible probability of rejecting the null hypothesis when it's really true. This is what that significance level is about. It gives us the probability of rejecting when it's really true. Okay? And that's why we choose a very, very small significance level like 0.01, which is 1%, or 0.05, which is 5%, or 0.10, which is 10%. We try to make sure that that probability is really small. But the other kind of mistake is, what if we failed to reject the null hypothesis? We don't reject it when it really is false. So these are the two mistakes. And again, this is all about that significance level. So some of you are like, well, Mr. Armstrong, if we want to make sure that we don't reject when it's really true, why don't we just make that 0? Okay. Well, I want you to understand, between these two, it's a give and take relationship. Okay. When you lower the probability of one, you increase the probability of the other, and vice versa. Okay. The book does a really good job of explaining this give and take relationship. So I want to show you that example. It's really, really good. I mean, I copied this straight from the book because it explains it really well. So to understand the trade-off, think about the criminal justice system. The null hypothesis is the jury, okay? And we always know that as the jury, the defendant is innocent until proven guilty, okay? So our null hypothesis is the defendant is innocent. So let's talk about that first type of mistake, okay? So occurs when we convict the innocent, but we convict the innocent. So we basically say that they are guilty, but when in fact they're really not. Okay? So the probability of making that mistake is what we call the significance level, as I said. And then the second type in this example is when we free a person that is really guilty. Okay? So in this, we can make the significance level 0. Okay? So we don't want to convict an innocent man. And we can do that by making it 0, simply by saying everybody goes free. Every defendant is free. Okay? But if everyone goes free, then it's impossible to convict an innocent person because we will convict no one. It's impossible to convict a guilty person, okay, because we'll convict no one. Okay? But it's also impossible to convict an innocent person too, because again, we're going to convict no one. So, in other words, if we can't convict anyone, then the probability of a guilty person going free is 100%. So if you lower the significant level where we will never reject, we will always fail to reject, then you're letting in those that are guilty. Okay? But on the flip side, if we lower the probability of freeing guilty people to 0, then now that means we will convict 100% of them, but now we're getting every innocent person convicted. Okay? So what we do as statisticians is we balance this. And again, we balance that by increasing the sample size. When you increase the sample size, you increase the precision, which lets us be more in line with what we want, which is why we can have the significance level be 0.01, 0.05, and 0.10. Because as long as we increase this, it increases our precision. Okay. Remember, precision is, if you remember back to that golf piece, it's when all of our golf balls are being shot in the same area. Okay. So it's like, hopefully, all of our golf balls are going straight into the hole, but whenever we shoot, all of our golf balls, or whenever we putt, I should say, all of our golf balls are landing right in the same area. Hopefully it's landing in the hole, but if not, they're still all clumped together in one area. Okay? All right. So, larger sample size, that's why it's important. That's why we check that. Helps us reduce the two types of mistakes. Okay? All right, then there's this piece called statistical significance versus practical significance. Okay? Let me explain what statistical significance means. Statistical significance is when you reject the null hypothesis. And what that means is when we truly reject the null hypothesis, it means that the difference between the data estimated value for the parameter and the null hypothesis value for the parameter is so large that it cannot be convincingly explained by chance. Okay? There's such a significant difference that we have to reject. Okay? So when we reject, this is what we're really saying in a nutshell. The difference between our data estimated value for the parameter and the null hypothesis value for the parameter is so large that it cannot be convincingly explained by chance. Okay? Now, also with this, just because there is a statistical significance, okay, just because we reject doesn't always mean that the results are useful or meaningful. Okay? Just because we reject doesn't mean that it's necessarily meaningful or useful. All right? Practical significance is when the results are statistically significant and meaningful. So useful, in other words. So there's a difference between these two. Let me give you an example of what we mean by this statistical significance and being meaningful or not. Okay? Again, the book has a great example of this. It says, suppose that the proportion for people who get a certain type of cancer is 1 in 10 million. Okay? So that's pretty low, right? Not to worry about that. 1 divided by 10 million. Okay? That's your probability of getting this type of cancer. Now, statistical analysis has been performed and finds that people who talk on their cell phones every day have a statistically significant greater risk of getting cancer. Okay, of getting that cancer we were talking about, that's 1 in 10 million. In fact, it is doubled. Okay, your risk of getting that cancer is doubled. All right, now, let me ask you this. Because your risk of getting that cancer is doubled using your cell phone, therefore it's like more dangerous to use your cell phone, are you going to stop talking on your phone if your risk went from 1 in 10 million, and if I double that, it goes to 2 in 10 million? Are you going to change your habits because it went from 1 in 10 million to 2 in 10 million? That's doubling. No. Even, that's a pretty big change in your habit, not talking on your cell phone versus the pretty small change in the risk. 1 in 10 million versus 2 in 10 million. Still pretty low. Okay, so that's what we mean by saying that this is significantly, statistically significant, but not practical, because that 1 in 10 million to 2 in 10 million, that's not enough of a change to make me change my behavior. Okay, that's why it's a significant, statistically significant. There is evidence. Okay, but it's not as meaningful to me. It's not as useful because I'm not going to stop talking on my phone. Okay? So, therefore, what we just talked about was not practically significant. All right? Another piece, you do not change your hypotheses ever. Do not change your hypotheses ever. This is cheating. Okay? So what we say about this is, if you change the hypotheses to when, whether you're trying to reject or not reject, whatever you're looking for, if you're changing your hypotheses to when, then that means you are increasing the significance level. By changing your hypotheses after you notice that, oh, if I did this, we wouldn't reject, or if I did this, we would reject. Okay? If you change because you see some observation like that, then you are not keeping to your original significance level. You are increasing it. So just so you know, we never ever change the hypotheses once we establish it in step 1. It's set. Do not change. Okay? Other things, I need to correct some vocabulary that I said. In 8.2, I talked about how in the interpret we either reject or accept. I need you to know that we never ever use the word accept. Using the word accept is like saying proved. That we have proved that the null hypothesis is awesome, okay, or true. Just so you know, proving in math means that it's very, very precise and very definite. Okay, if you prove something, you are saying it is absolutely and positively, without a doubt, true. And that's the same thing as when you say accept. Okay, accept is like saying without a doubt this is true. So we do not accept or say that we proved the null hypothesis. Okay? What we do, and what hypothesis testing is doing, is that it is demonstrated or showed something. Okay? It has demonstrated or showed something. What that means is, we do not say we accept or prove the null hypothesis, but we say that we cannot reject. We have shown or demonstrated that we will not reject the null hypothesis, or that we failed to reject. This is another way to state it. Or state it this way: there is insufficient evidence to reject. Okay? So we never say we accept. We say we cannot reject. We failed to reject. There is insufficient evidence to reject. Because when you say we accepted, that means you are telling me without a doubt that this is true. Always. Okay? All right. And please know that hypothesis testing is all about demonstrating or showing something. Okay? All right. And then last but not least, I want you to know that confidence intervals and hypothesis testing do kind of relate to each other. Okay? They just answer different questions. When you do confidence intervals, you're actually answering the question, what is the value of the parameter? What is the population parameter? That's what confidence intervals answer. In hypothesis testing, you are asking the question, are the data consistent with the parameter being one particular value? That's your null hypothesis. Or might the parameter be something else? That's the alternative hypothesis. So your question is, are you saying the data matches the null, or does the data say it's something else? That's what you're answering with the hypothesis testing. Now, how do they relate? Simple. And again, I like using the book. The book does a great job. I love the book stuff. So right here, even though they answer different questions, they are similar, okay? Because you can reach the same types of conclusions you would reach with the hypothesis test using a two-sided alternative hypothesis. So if you're doing the two-sided alternative hypothesis, you can get the same answer, okay? It only works with the two-sided, just so you know. In most situations, doing a hypothesis test with a two-sided tail, okay, and a significance level will lead to the same conclusion as finding the confidence interval minus the significance. Okay? So think about this. Our default is 0.05 as a significance level. If I take 1 minus that, I get 0.95. That's a 95% confidence level. Okay? And so if you run the two-tailed, if you run the confidence interval of 95%, or the confidence level, confidence level of 95% and find the confidence interval, if the null hypothesis is in that interval, you're going to not reject the null hypothesis. Okay? If the null hypothesis is not in that interval, then you will reject the null hypothesis. Okay? So that's how they're closely related, because it's just like a two-sided tail. Remember that if you look at the pictures of these, the two-sided tail looks like this. The confidence interval diagram would look like this. So you can see how your null hypothesis, if it's in this confidence interval, okay, so this is the hypothesis test. This is the confidence interval. If your null hypothesis is in here, then you're going to not reject the null hypothesis. But if that null hypothesis was outside of this, then that's where you will reject. Okay? So you can see that it's kind of like the yin and the yang to each other. The hypothesis test is the outside of the center of our confidence interval that we would shade. Okay? All right. So here we've got a question. So it says a researcher carried out a hypothesis test using two-sided alternative hypothesis. Which of the following z-scores is associated with the smallest p-value? And pause and go. Okay, remember I talked about this. The more extreme the z-score, the smaller the p-value. So you just got to look and see who has the largest z-score. And that would be this one. And right there, what I just said to you is the reason for it. Okay? The larger the z-score, the smaller the p-value. And that is the largest z-score. All right? Another example. And this is actually the last one. There's more questions over, what we just talked about in general than there are like where you're actually doing examples. All right. So on this one, I'm going to actually give you the entire page on this. It says a test is conducted in which a coin is flipped 30 times to test whether the coin is unbiased. The null hypothesis is that the coin is fair. The alternative hypothesis is that the coin is not fair. Okay? So if we're thinking about the null hypothesis, that means P is equal to 0.5 because there's only two sides. The alternative hypothesis, when they said is not fair, would be P not equal to 0.5. Okay? One of the accompanying figures represents the p-value after getting 16 heads out of 30 flips. The other represents getting 18 heads out of 30 flips. Which is which, and how do you know? All right, so pause the video and figure it out. Go. All right. So, when you're looking at this, the 16 divided by 30. If you actually did just a little bit of quick math there, and you took 16 divided by 30, you got 0.53 repeating. If you take 18 divided by 30, just a little bit larger of a numerator, you got 0.6. Here is which graph is which. This one is the 16. This one represents the 18. How do I know that? The closer I am to this p-value, the null hypothesis, the smaller your z-score is going to be. Okay? The closer you are to this, the smaller your z-score is going to be. The further you are away from this, the larger the z-score. Because remember, even though this is on a normal distribution, we can always go back to the original where we say, you know, this is 15 out and as our mean, okay? And then we use our standard deviation to move out from there, okay? So in the middle represents like 15 out of 30. That's half, okay? 16 is closer to 15 than 18. So that means the 16 is going to have the smaller z-score because it's closer to the 15. The 18 will have a larger z-score because it's further away from the middle, where 15 would lie, because that would be 50%. Okay? And so that's how I know which one is which. All right? Hopefully that makes sense. The closer you are to the null hypothesis, the smaller your z-score. The further you are away from this, the larger the z-score. Okay? All right. So your questions fall from in the assignment for Chapter 8, questions 43 through 47. Again, those are the two application type questions. Everything else is about the information that we talked about before. You're not really applying it. You're just, making sure that you understood what we just went through. And that is section 8.3. I will see you next time for 8.4.